In the last video, we looked at how we could write functions that take other functions as input, and this was a useful way of turning functions that do a specialized job into functions that do a generic job. Now, the examples we looked at in the last video were kind of tiny, so now I'm going to show you two major examples of very useful generic functions that we can make by generalizing more specialized functions. So here I'm going to write a function which takes a list of integers and it doubles every integer in the list. So let's write this. So it takes the empty list to the empty list, and it takes a list that has head x and tail x's, and returns a list where we multiply the head by 2, and then we carry on and double all of the rest of the list. So let's see how this works. We double all 1, 2, 3, 4, 5, and we get 2, 4, 6, 8, 10. Now we can use the same process that I did last time, where we generalized double to apply a different function to the same argument twice. And we can do the same thing here. We can notice that we might have always want to do something to every element of a list. So we might want to add 2 or multiply by 4 here. But this general pattern of doing something to every element of a list is a generally useful one. So what I'm going to do is take this function double all 0 and generalize it by replacing what happens to every element of the list. So here it was times 2, but I'm going to replace it with a function. So this is going to be map. It's going to take a function f, and on the empty list it still returns the empty list. On a list with head x and tail x's, then instead of multiplying by 2, we're going to take f and apply it to x. And then we're going to carry on doing map f to the rest of x's. So notice here that we have to supply this argument f again back to map, so when it calls itself recursively. Now what's the type of this function? Let's see if we can work it out. So we don't know what the type of f is yet, so let's just put a question mark there for now. And we're going to take a list as input. So the second argument is a list. And before it was integers, but now we're not making any commitment to what the type of the values in the list are. So it's just going to be a. And likewise, when we output, I mean, it could be a, but we could think, well, f, what's that going to do? It's going to take values of type a, and should be no restriction on what type of values it should output. So we're going to output a type of list b. And so, following that reasoning, f is going to have type a arrow b. So f takes a's and gives you b's. And then what does map do? It returns a function which takes a list of a's and gives you back a list of b's. So let's load that in. And now we can try this with map double from the previous video, 1, 2, 3, 4, 5, and we get 2, 4, 6, 8, 10. So what's happened here is that we've written map with double on a list 1, 2, 3, 4, 5, and now it's a bit more complicated to unfurl this because it's a recursive function, but what's really going on is that it looks to see if this is the empty list. No, it isn't, so it looks to see if it has a head, and then we do the second line here, so it's going to be double 1 followed by applying map double to 2, 3, 4, 5. And then this is going to carry on. We'll end up with double 1 followed by double 2 and then map double 3, 4, 5 and so on until we get down to doubling 1 is going to be 2, doubling 2 is going to be 4, and so on for the rest of the list. And indeed, we can rewrite our definition of double all now just in terms of map. So we can say it's a function from int to int, and double all is just map double. Now the advantage of this over writing the original definition of double all that you can see at the top of the screen is that we can immediately see that it applies a function to every element of the list. It doesn't do anything complicated, like based on what the length of the list is. And immediately you can see that all it does is take every element of the list and apply double to them individually. So it doesn't try to add up the length of the list or keep a running total or anything like that. So there are many, many applications of map. And one way to think of this is that map lifts a function from being just on individual data values to being a function on lists. And just here's some quick examples. So we might have a list of pairs, and we just want to get the first one out from every pair. And we can just write this as map first. And let's give that a go. So we've got firsts, and let's say we've got a list of key value pairs, and we just want to get the keys, and we can just use firsts on this. So we've got key 1 is associated with 1, key 2 is associated with 2, and then we'll just get as key 1, key 2. And likewise, we could write seconds to get all the values. We can also do some processing where we add information to every element. So for example, with lengths, we're going to do map, and now we don't have a function at the moment which takes a string and returns the string itself with its length, but we can use the lambda notation to write one quickly. So we can just say you need a function that takes an s, and it returns the string s along with the length of s. And now we have a function which augments a list of strings with their lengths. So then we can use this one we had before. First I have to reload the file. We can use this computation we had before, so it takes all the keys, and then we can just ask what's the lengths of all the keys. And that will give us the key 1 as length 4 and key 2 as length 4. Another useful generic function that's a bit like map is filtering lists. So let's write out another specialized function and see how to generalize it to this. So we want a function which just checks for all the even, just returns all the even elements in a list. So how's this going to work? So again, finding the even elements in the empty list just gives us the empty list. Finding the even elements in a list with head x and tail x's, well, that depends on whether x itself is even. And the easiest way to check this is this function mod. So what mod does is it divides its first argument by its second and gives you the remainder. So this one is going to take x divided by 2, and if the remainder is 0, then we know that x is even. So if it is even, then we want to return it in the output and then get the only evens from the rest of the list. Otherwise, we just want the only evens from the rest of the list. So let's see if this works. Oops. Only evens 0. So let's see if this works. We've got only evens 1, 2, 3, 4, 5. So we should return 2 and 4. Right? So it only returns even ones. So again, this is a kind of thing that we might expect to be a generic pattern. We've got, we're recursing down a list, we're doing some test on every element of the list, and then we're keeping it if the test passes, and throwing it away if the test fails. And indeed, this pattern has been given a name, filter. So we're going to take a function that I'm going to call p for predicate, this is the thing that's being tested. And just as with only evens, we're going to write that filter on the empty list returns the empty list. And filter on a list with head x and tail x's is going to do what only evens did, but just with the generic predicate p rather than the test for evenness. So we're just going to say if p of x is true, then we keep x, and we carry on filtering the rest of the list with p, else we just filter the rest of the list with p and don't return x. And what's the type of this? Well, similar to map, we want this to be generic, so it doesn't just work for integers. So we're going to take an a, and this time it has to return a bool because we're using it in an if then else. And then because we are copying the input values to the output, then the type of the output has to be the same as the type of the input. So filter is going to have this type. And then we can write our function, only evens, again using an anonymous function. We can say x mod 2 is equal to 0. Apply that to 1, 2, 3, 4, 5, and again we get 2, 4. And then we can make that into a definition itself. Only evens int list of int to list of ints, and we can say only evens is filtering on the predicate which tells us whether an element is even. And then we could test that to see that it gives the same answer as before. So what's happened here is exactly the same process as before. We've taken a specific function, which just did one job to a list, generalized it by taking out this specific part here that checked for evenness, and replaced it with a predicate p, which is passed in as an argument to the function. And now, again, as with map, we can see that only evens, the definition here my cursor is on, is a bit clearer, in my opinion, than only even 0, because it's hidden all of the machinery of doing the recursion and building up the list and everything, and explicitly says we're filtering to just the things which are even. And we could even make this a bit clearer by writing it out as is even, and then using a where clause to define this function as is even, like this. We can also use filter to rewrite the quicksort function to be a little nicer and not use the list comprehensions. So we can use this to generate these smaller and larger functions. So rather than using these list comprehensions, we could write filter, take in a y. We want all the y's which are less than x from x's. So that replaces this list comprehension. And filter, take all the y's where y is greater than or equal to x from x's. So it's up to you which one of these you think is nicer, but I think using filter is a bit nicer because it avoids all the punctuation symbols in the list comprehension notation. And oops. So I'm sorry, I made a syntax error here, so I'll just get rid of that. Close bracket. Reload, and then we can check that qsort actually sorts the list back into order. So in summary for this video, I've shown you map, which is a generic function from lifting a function on items to a function on lists of items. And filter is a generic function for only keeping some items in a list. And these two functions are extremely useful for writing simple data processing applications. And the key point here is that both are customizable patterns of recursion. So we don't have to keep writing the same kind of pattern of recursion where we say the empty list goes to the empty list and the list with the head x, then we do something to x and then we do something to the rest of the list. We can customize these. We can use these simple patterns of recursion, package them up as map and filter, and then customize them by supplying the right arguments.